Okay, 6, 7. Rates of change again, this time in trigonometric functions. As the title suggests, there's not a lot new today. The only difference is we're looking at trigonometric functions. So we're going to examine the average and instantaneous rates of change in trigonometric functions. So here we have a time versus distance graph. This was done using a motion detector. She stood in front of a child and recorded the distance. It's measured the horizontal distance of her child and a child when she's on a swing. She stood in front of the child and recorded the distance in meters over a period of time, t in seconds. The data she collected are given in the following tables and shown on the graph below. So you can imagine a child swinging him back and forth on a swing. And here's your motion detector. Okay, so this swing is going like this, towards, and then away. Alright, so we have the distance from the motion sensor then becoming further and closer. So right here, this is the closest position right there, and up here at the top, it's the furthest away. Okay, so our time in seconds, we can see it takes about 1 second, or 0.8 seconds, to go from the furthest away to the closest to the motion detector. How did the speed of the child change as the child swung back and forth? So the speed is actually dictated by what? How can we figure out the speed? If this is a distance time graph, how do we know what is the speed if we're talking about speed? Gianluca? Sorry, yeah, you're right. It's distance over time, but then what did you say? I still didn't hear you. What?
Look at the points on the graph.
Okay, look at the points on the graph, right? But what do we have to do with those points? It's a little bit more than that, not much, yeah.
We have to find the slope.
Yeah, we take the slope, right? Because it's distance over time. So the slope at any given point will give us the speed, right? So we're going to look at kind of instantaneous speeds. So the way we find those is we take the slope of the tangent, right? If we want to look at average speeds, we take the slope of the secant. Does that make sense? So the average speed then over, say 0.8 seconds and 0 seconds, you would draw a dot here and a dot here, connect them and get that slope. The instantaneous speed at 0.5 seconds, you would draw a dot at 0.5 and draw a tangent line to that dot and take the slope of that tangent line. Okay, so that's what today's lesson is all about. So it says, use the data in the graph to discuss how the speed of the child changed as the child swung back and forth. Analyze the motion. So we can analyze the instantaneous velocity by drawing tangent lines at various points over one swing. So if we draw all these points here along the curve, and it's tough to see, I'll zoom in a little bit more. Okay, so we've drawn 1, 2, 3, 4 points here. And it's almost a straight line here, but there is a curvature to it, right? So what we'll see is when we draw those tangent lines, so there's 4 points down here. It's slight, but it does change, right? As it approaches the maximum or minimum points on the curve, the tangent line is actually becoming smaller and smaller, or the slope of the tangent becomes smaller and smaller. You guys see that? Until when we get to the top, if we were to take a tangent at this point here, it would be 0. Okay? So slope of tangent here is equal to 0. So what that tells us then is at this point in time, what's happening on the swing? What's actually happening? Yeah, she's stopping, right? So she's swinging one direction. She's getting to the maximum or minimum point of the swing, stopping and then going back the other way. Okay? So as you approach that point, you're also slowing down. So here's your tangent lines, steeper, and they're slowing down as they approach that point. Okay? So you can see that here. So here they're starting far away. She's coming towards the motion detector, towards the person that's filming this. And as she gets closer and closer and closer, it comes to a stop and then turns away and starts moving away from the camera or the motion detector. Okay? So towards, away, towards, away. And speeding up, slowing down. Speeding up, slowing down. Speeding up, slowing down. That's the idea. Okay? So between 1.2 and 1.6, the child's speed was decreasing. So 1.2, which is here, and 1.6, between these points, she starts to slow down. So in other words, the slope of the tangent here is becoming less and less, or more and more horizontal, slowing down. Okay? Any questions what's happening on this graph? I think it's pretty straightforward. Explain how the data in the table indicates the direction in which the child swung. All right, well, if we look at the data in the table, we can see that as the time goes, initially the distance gets closer and closer, or less and less. So we know that the child is becoming closer and closer to the motion detector as this distance gets smaller and smaller. As the distance gets larger and larger, then that means the child is swinging away. So x values larger. Explain how the slope of each tangent line indicates the direction in which the child swung. So if we take the slope of this tangent line, so this is when she's moving towards, right? Because the distance is getting smaller and smaller. The slope of this tangent is what? Positive or negative? Negative. So the direction as you approach the camera, the slope becomes negative. Why? Because the distance is decreasing. The distance is becoming smaller and smaller. As you move away from the camera, the slope, of course, is going to be positive. Okay? Any questions there? All right. How can you tell from the graph when the speed of the child was 0 meters squared? This is when slope is equal to 0. So max or minimum points. D. If someone began to push the child after 2.4 seconds, describe what effect this would have on the distance versus time graph. What would happen? At 2.4, okay, what's the end of the graph? What happens if now we start pushing the child?
Faster, closer to the camera or farther?
Yes. You guys understand that, right? Because there's going to be more force. So what's actually going to happen in reality then is the altitude will get higher, right?
Would it also be like compressed a bit?
No, it wouldn't, because it would take longer for them to go further out.
Oh.
So the period, I think, would stay the same. All right, example 2. Calculate the child's average speed over the intervals of time as the child swung toward and away from the motion detector. So average speed as they swung towards, so this is going towards, we're going to take the 2 points at the ends. So at time equals 0 and time equals to 1, we draw 2 points, we draw a line, and we take the slope. So here's our interval between 0 and 0.8. Our distance is 0.6 minus 0.38 over our time, which is 0.8 minus 0. Where do these numbers come from? They're right here. So 0.6, which is down here, and 0.38, which is up here. Okay, y2 minus y1. Okay, so you take this point, we take this point, we draw a line, and then we take this and this, y2 minus y1 over x2 minus x1. And we get our average slope, or speed. The average speed in both directions. If we did the same thing on the other side as they're moving away, we would take these 2 points, and what we find is we get the same value, but this time it's positive, because the distance is getting larger. All right. Next example. Use the difference quotient to estimate the instantaneous rates of change. Okay, so to model the motion of the child, Melissa determined that she could use the equation this Good of you guys came up with this equation? I hope so, right? And I'm surprised that they gave it to you in this question. When the very last section, that's all we did is we took a graph and we came up with equations. So this, you should be able to see that you can find this value, you can find this value just by looking at the maximum and minimum points of the graph. Okay, and then you find this value by translating it. Okay. So we come up with the equation and then we ask, use this equation to estimate when the child was moving the fastest and what speed the child was moving at this time. Okay, so when the child is moving the fastest, we know the slope is the steepest. So the slope is going to be the steepest right in the middle between the max and the minimum, right? Because once we pass this middle, we start to slow down. Once we're before that, we're speeding up and then we're slowing down. So it's this point where it's the fastest. So really what this is asking then is what is the instantaneous rate of change when t equals 0.4, or the middle of the graph between the maximum and minimum, okay? So first we can try and find the average rate of change. So we draw a tangent line and then we pick 2 points and we find out that it's 6 or -6. But then if we want to get the instantaneous, really what we should do is use the difference quotient. So that's what we do here. We let h equal 0.001 and we look at the point of 0.4. T equals 0.4 and then one small number of h, 0.001. So we actually get this value, -6.28. So it's negative here, it's positive here. We're going to get positive 6.28 on the other side. So this whole difference quotient here now is the exact same way we've used it before. Now we're just plugging it into the trigonometric equation, which is way up here. Okay, and finding our y value. You guys see that? So it's used the exact same way. The only thing I would caution you guys is that you make sure you put in these brackets. If you don't, you might not switch this sign to a negative. You guys see that? That's going to be an area where a lot of people mess up. Okay? So you're just plugging into the equation 4.401 and 0.4. But you have to make sure when you subtract, you keep everything in brackets, and that subtraction now gets distributed. So exact same process. Here we do the exact same thing, but this time as the child's moving away, we get the same answer. So if we do the secant line, we get an average of 6. If we do a difference of quotient, we get 6.28. Okay, so it's the exact same thing. Anybody know the problem with this graph? What's unrealistic about it?
The fact that he's always moving the same speed.
Okay, yeah, I think I know what you mean. Not so much the same speed, but no, he wouldn't move further away.
When you pump on a swing, you change your...
Sorry?
Should the amplitude be decreasing?
Yes, exactly. Should be going like this, right? Should really be going like that.
Because you're losing energy.
Right?
You can't constantly stay at the same speed.
Isn't that assuming that he's not putting in any work?
Yeah, but it doesn't say in the question that he's continuing to be pushed.
It doesn't say that he's not.
And even
True.
And even if he is getting pushed, then you need one.
There would still be like little dips like that, right?
Yeah.
It would still go down and then up, right? Anyways, thought that was interesting. They don't mention it either way. All right, there's our difference equation. Here is like the whole lesson, right? Here, this is everything right here. Just taking the value, plugging it into the difference quotient for trigonometric functions. There's no difference except for the fact that this equation is a little bit more complicated than what we're used to with typical polynomials. Okay, that's it. So in summary, the average and instantaneous rates of change of sinusoidal functions can be determined using the same strategies that were used for other types of functions. So this is a review, right? Review with more complex functions. That's it. All the principles are the same. The tangent lines at the maximum and minimum values of the sinusoidal function are horizontal. Since the slope of a horizontal line is 0, the instantaneous rate of change at these points is 0. That's important, right? If we take a tangent line, this slope is going to be 0. In a sinusoidal function, the slope of a tangent line is the least at the point that lies halfway between the maximum and minimum values. That's important. Okay? It says it's the least. I think of it as the greatest, right? It says it's the least because it's going down. That's why they say the least here. So it's the least, so it's the most negative when it's moving away, and then they counter that with, they say it's the most. The slope is the greatest at the point that lies halfway between the minimum and maximum values. I would just say this. The absolute value of the slope is maximum Okay, all that's saying then is your slope is the maximum here. Any questions about that point? It's a little confusing how they worded it. They said it's the least because it's the most negative. That's what they mean by the least. The appropriate approximate value of the instantaneous rate of change can be determined using one of the following strategies. Sketch and approximate tangent lines on the graph and estimated slope using 2 points that lie on the secant line. So what that means is you draw the tangent line. If I were to do it down here, you draw the tangent line, and then you take points on that tangent line and use these 2 points to calculate the slope of the tangent line. Okay? Obviously, that's not as good as doing it algebraically, as we can find an exact value if we use the difference quotient. Using 2 points in the table of values, preferably 2 points that lie on either side or as close as possible to the tangent point to calculate the slope of the corresponding secant line. So you would take your table of values, you would look at your point of interest, which was 0.4, and you would calculate using the 2 points on either side. Again, that's going to give you an approximation. Finally, the last one, using the defining equation of the trigonometric function and a very small interval. So this is, of course, as we know, the difference quotient. And it's your best option for the most accurate answer. Any questions?